In this video we're going to introduce a new unit for the measurement of angles. In our everyday lives we are used to the fact that distances can be measured in miles or in kilometres, and know that we can convert between the two systems of units using one of the approximate relationships. 5 miles is approximately 8 kilometres, or 1 mile is approximately 1.6 kilometres, or 0.625 miles is approximately 1 kilometre. So far in our mathematics, angles have been measured using degrees, and the division of a circle into 360 parts, known as a degree, is thought to be due to the ancient Babylonian civilization, who thought that a year was divided into 360 days. In the early 18th century, the radian was introduced as a unit for angular measurements, and it will be seen that the use of the radian for angle measurements has many advantages in mathematics beyond this point. If we look at the video now, we can see that we've got a circle of radius 5 centimetres, and the arc AB subtends an angle of 78.28 degrees at the centre of the circle. So the length of the arc AB will be the fraction of the circle that we've got times by the circumference of the circle, or 78.28 divided by 360, which is the fraction of the circle that we've got, times by 2 times pi times 5, which is the circumference of the whole circle. If we now allow the angle to decrease slowly, we find that the arc length decreases, and when we get to an angle of 57.3 degrees, we see that the arc length is very, very close to being the same as the radius. 1 radian is defined to be the angle at the centre of a circle made by an arc of the circle whose length is the same as the radius of the circle. So the video that we've just seen tells us that 1 radian is approximately 57.3 degrees. We can find a more exact value for 1 radian in degrees by supposing that 1 radian is equal to theta degrees, in which case the arc joining A to B has got to equal the radius of the circle, which means that we've got the equation r equals the arc length, but the arc length will be the fraction of the circle that we've got, which is theta divided by 360 times by the circumference of the whole circle. So we've got r equals theta over 360 times by 2 pi r, which simplifies to r equals pi times r times theta divided by 180. The r's cancel out, and if I rearrange that to make theta the subject, I get theta is equal to 180 divided by pi, or approximately theta is 57.296 degrees. So we've found out that 1 radian is exactly the same as 180 divided by pi degrees, or 1 radian is approximately 57.296 degrees. Keeping in mind that 1 radian is exactly the same as 180 divided by pi degrees, we could rewrite that as saying that pi radians is exactly the same thing as 180 degrees, or we could say that 1 degree is the same thing as pi divided by 180 radians. The accepted abbreviation for radians is rad. So these three statements that we've got would become 1 rad equals 180 over pi degrees, pi rad equals 180 degrees, or pi over 180 rad equals 1 degree. So if we've got 65 degrees, we can say that 65 degrees is the same thing as 65 times 1 degree. So that's the same thing as 65 times pi over 180 radians, which is exactly 13 over 36 pi radians, or 1.134 radians approximately. Similarly, if we've got 2.85 radians as an angle, and we wish to find it in degrees, we can say that 2.85 radians is the same thing as 2.85 times 1 radian, so it's the same thing as 2.85 times 180 over pi, or approximately 163.3 degrees. So we know how to convert between degrees and radians, and vice versa. The fact that pi radians is exactly the same thing as 180 degrees immediately gives me some important exact results. For instance, it gives me that 2 pi radians is exactly the same as 360 degrees, that 4 pi radians is 720 degrees, that pi by 2 radians is 90 degrees, that pi by 4 radians is exactly the same thing as 45 degrees, that pi by 6 radians is exactly the same thing as 30 degrees, and that 2 pi divided by 3 radians is exactly the same as 120 degrees. And there are lots more results of that form that we can get for exact conversions between radians and degrees. If we are measuring in radians, then the formula for the length of an arc of a circle becomes really neat, because we know that a full circle is 360 degrees, and 360 degrees is 2 pi radians. So the fraction of the circle that we've got is theta divided by 2 pi. So the arc length that we've got is going to be the fraction of the circle times by the circumference of the circle. So we can say that the arc length is theta divided by 2 pi times by 2 pi r, which simplifies dramatically to give me that the arc length is r times theta, provided we are measuring the angle theta in radians. Similarly, the sector area is going to be the fraction of the circle we've got times by the area of the whole circle. So the sector area, if we've got a sector that subtends an angle theta radians at the centre, is going to be given by theta divided by 2 pi, the fraction of the circle, times by pi r squared. And that simplifies to a half of r squared theta. So provided we're using radians as our angle measurement, we've got sector area is 1/2 r squared theta. Notice how much simpler these two formulae for arc length and sector area are if we are using radians for the angle rather than if we're using degrees for the angle. So we're now going to look at a couple of examples involving radians and arc lengths and sector areas, but where the angles are given in radians. So for the first example, we've got to find the perimeter and area of the sector of a circle of radius 9.5 centimeters that subtends an angle of 1.2 radians at the center of the circle. The perimeter of the shaded region then is going to be the radius OA plus the arc AB plus the radius OB. So we've got the perimeter is going to be 9.5 plus 9.5 plus the length of the arc AB. But because we're using radians, we know that arc is given by r times theta. So we've got the perimeter is 19 from the 2 times 9.5 plus r times theta, which is 9.5 times 1.2, which gives me 30.4 centimetres. The area of the region is simply the sector area, so that is given by a half times by r squared times by theta, which is a half times 9.5 squared times 1.2, which gives me 54.15 centimetres squared. And in the second example, we've got the arc of a circle has got length 15 centimetres, and the area of the sector formed by this arc and the two radii is 45 centimetres squared. We've got to find the radius of the circle and the angle in radians subtended by the arc. So the fact that the arc has got length 15 centimetres means that I can say that r times theta has got to equal 15. The fact that the area of the sector is 45 centimetres squared tells me that a half r squared theta must equal 45. Or in other words, that I've got r squared theta must equal 90. But r squared theta, of course, is simply r times by r theta. And I know that r theta is 15. So I've got r times by 15 equals 90. So r must equal 6 centimetres. And if r equals 6 centimetres, then I must have, from equation 1, theta equaling 2.5 radians. So that concludes our introduction to the use of radians for measuring angles.